Hey, good morning, Ahadu. Thank you for taking the time to speak with me today. Can you please tell us a bit about yourself and your schooling?
My name is Ahadu Assegued. I'm now entering my fourth year of engineering. I study aerospace engineering, and I've been involved with Engineers Without Borders since my first week at ASU, so 3 years now. I joined our Ethiopia project where we do plastic recycling. And so we build machines that shred, wash, dry, and then injection mold plastic pellets into all sorts of products. And so I've been a team lead since my sophomore year, and then recently I became president of the club, where I mostly take care of finding new projects, new partners, and ways of hosting events, all sorts of things, sponsorships. Yeah.
For you, Professor Saurav, can you tell us a bit about yourself and Ahadu and how you all connected through the STELLA project and all that?
Sure. I am Saurav Kumar. I'm an assistant professor in the School of Sustainable Engineering and Built Environment in the Ida Fulton College of Engineering at Arizona State University. So my research group has been working on using Earth observations for various types of decision making and hyperspectral imaging. Ahadu connected with us through something called a Fury project. That's an initiative at Arizona State University to get undergraduate students engaged in research. And Ahadu was really interested in trying to understand how satellite data and Earth observation in general can be used uh, for land use land cover change and other ideas around water quality. So and really that is the time I had met you, Taylor, and we were Michael, and we were trying to figure out that how Stella may be a cool, nice thing, a nice educational and even research tool. And as we know, some of the problems that we have around using Earth observation is lack of data, especially in inland waters and things like that. So I proposed to Ahadu that maybe he can use it. So there was a student before Ahadu who was making the Stella based on your designs. I think it was the early design 1.1. And so Ahadu thought that was a good idea, and we wrote a small proposal, and we got funded for 2 years. So that's really how I got in touch with Ahadu and how he has been doing this.
Well, I want to thank you both, and your email attached poster provided a fantastic overview of this research. And to really kick things off, I'd like to hand the floor over to you, Ahadu.
I've always found uh, remote sensing an interesting subject. It was something, and Earth observation. It was always something I wanted to get involved in for graduate school, and I think that's also why I chose aerospace engineering. And so from there, when I reached out to Dr. Kumar, I had the opportunity to work on Stella, and we worked on the Stella 1.1 device, with the Stella 1.1 device, where we focused on collecting water and soil quality data using Stella and then comparing it with a hyperspectral imager. And the goal was to see if there's overlap and similarities between what I get with Stella and the hyperspectral imager, knowing that the imager is a lot more accurate and And so whereas Stella has higher margins of error. And the goal of the project is to see how much of this error can be, how much of the Stella data is accurate enough. And so I've mostly been going on the field, collecting spinach leaves and their reflectance data. And I did the same with algae in the lab and on the field. And I compared it with what I got with the hyperspectral imager to see if there's any similarities between the two. Right now, we found trends that overlap. And the next goal is to see if we can actually quantify how accurate Stella is compared to the imager. And that's my, I think, goal for the next semester.
That's awesome. And you should know that just briefly before you got on, I was talking to Dr. Kumar, and I let him know about the 1.1 and that we had, or I should say, I keep saying we, but one of our collaborators, Colorado State University, has found a bit of a flaw with the infrared with the integration time. I sent a link to the GitHub with their finding. We would need to reprogram it in there and all that, but it might affect some of your readings a bit, depending on what it is. But it's only for the near infrared, not for the visible.
Getting to understand all the details which Ahadu is doing right now, like working how the integration time works and how those things work, is really helping him leaps and bounds to understand how like the spectral images eventually how they work.
So in the poster, you noted the consistency in spectral trends between STELLA and the high-fidelity HySpex imager, despite the noise. Could you describe a specific example from your analysis, either with the algae or the spinach, where you saw this consistency and what that finding implies about the practical use for a low-cost sensor?
Yeah. So in the case of the spinach, when we went on the field, what we found was that we were able to see, because it's 12 bands with STELLA, we have 12 bands with STELLA, we're able to see how it progresses with the wavelengths and find a bit of overlap with the same groups that we're targeting, and with the different groups we were targeting. And so with the hyperspectral imager, we would see the line and we would see the data points be similar to what we found with the imager. Additionally, when we let me grab it right here. When we focus on different groups. So a first group had no amendments. A second one we had a control group. Okay, so let me restart this. Sorry. So when we studied the spinach, we had it was an ASU PhD student that was working on seeing how cadmium affects spinach leaves. And so and if we're able to pick up this behavior with the hyperspectral imager or STELLA. And so we had different groups of spinach leaves that had a certain amount that had amendments to fight off the cadmium, or had no cadmium at all, or had cadmium without any amendments. So I focused on collecting data from our control group, which is the cadmium-free spinach, and then the amendment-free cadmium-affected spinach. And so when we're collecting the data, we're able to see that general trends where we'd have the lines with the hyperspectral imager and then STELLA data points overlapping with those specific lines. Similarly with the algae, we had a group, we worked in the lab where we collected reflectance data for toxic algae and then non-toxic algae. And then with the algae, what we're able to notice is that at around 650 nanometers, we were able to see a slight peak for the toxic algae in reflectance, and then a drop for the non-toxic algae. And STELLA was a bit able to pick this up. And so now the next goal is to see how much accurate it is, if it's any noise, if it's just random luck. But I believe that the trends are there, but we still have to see.
And you astutely identified the sensor's radiometric quality and band design as likely sources of the noise. From an engineering standpoint, if you were tasked with briefing the STELLA 1.2 development team, what's the single most important improvement you would advocate for, and what trade-offs would you be willing to accept to achieve it?
I would maybe say be able to have more bands, especially in the near infrared section. I think in the case of STELLA 1.1, we had around 12 bands. And when we're comparing it to a hyperspectral imager, because we got a whole line, it can be a bit confusing because we have increments for the data point. So it goes from 550, if I'm not wrong, to 610, and then 680. And so we can't really see what's in between. But so yeah, maybe get a few more bands, and then correct me if I'm wrong, but I think it's also the bandwidth being a bit too large. If we're able to maybe find a sensor that has a smaller bandwidth, we'll be able to get more precise data for the specific wavelength. Yeah, I guess the trade-off would be cost.
Can I ask you a question? Can I prompt you something here? Because we struggled a bunch with some simple stuff about where are we focusing on the leaf, or are we? There's just simple stuff. It's not really very fancy, like hardware constrained thing. It's just engineering issue of how much pure pixel are we getting? Is it there's a pure pixel of what we're getting or not? So if there, I could see if you could put a LED or something which kind of gives you the, or a laser thing which gives you the area of cone where you're getting it. It would be tremendously helpful. But I know it will kind of, I don't know, maybe we turn it on and off because you don't want it to be picked back up, whatever the laser light is on. But I was thinking that would be a cool thing to add some laser lights and see where the cone is or project it so that you know that you're actually getting what you're looking at.
Yeah, because I think that was the biggest challenge I had with the Spinach Leaves was because they were just starting to grow, I had to get very close to the leaves themselves. And so sometimes I don't know if I'm getting soil data or if I'm actually getting the leaves. But yeah, there's that. I know that there's a 3D printed housing that you can fix on top of it. But what I noticed is that it was way too high. So I wasn't able really to get a good idea of how much of the cone was projected because I would get really close to the leaves.
So you worked with data from a handheld sensor, an aerial imager, a satellite, with significant data integration challenge. What was the most difficult part of harmonizing those data sets in MATLAB to ensure you were making valid apples to apples comparisons?
The hardest part was processing the different sources of the different data sets that come from different sources. So I would get data from Planet Labs, for example, and I would be required to use Python, which I'm not good at all at. And then I would have to take the data from the hyperspectral imager, which I think it required us to use 7 different softwares up to, I think, 5 at one point. And then making sure that once I get all these data sets that I have the right values that I need, that I didn't mess up anything. STELLA is very easy to work with by far. I think STELLA is by far the easiest. Data that I collected and processed, mostly because I would get everything on a CSV file. The rest of it was mostly getting all those huge data sets and converting them into a CSV file and then adding them to MATLAB. And it was pretty hard. Luckily, I had another PhD student, Mattis, who would help us a lot, and then my friend Miko, who also worked on the project with me. So that helped us get everything done on time. If not, it would have been a bit of a challenge.
That's fantastic. So you had bring in 2 others. Can you would you mind giving them? I know you gave them sort of a shout out, but like their full names, if you don't mind.
Yeah. So the first one, the PhD student, is Mattis Quorum, and then the second person was a good friend of mine. We did the 3 program together. It's Miko Dakota Roberts. Yeah. So we did. He took care of mostly processing all the data from the aerial hyperspectral imager into CSV files and then giving them out. But yeah.
So, but it also brings up a critical point about data quality, and I know we talked a little bit about this, but a vital step in collecting reliable spectral data is calibration. Could you walk me through your in-field calibration process for the STELLA sensor? For instance, I understand a folded weight sheet of paper was utilized as the weight reference. How frequently did you perform that calibration to account for changing sunlight conditions, especially when when your goal was to compare that data to the HySpex imager?
So I have a calibration plate, so it's 4 different plates with different colors, and so I would take what's most similar to the data I'm working with. So if I'm working with soil, for example, I would take a slightly darker color panel out of the 4. And usually I would start first by scanning the plates with the Stella, saving them, and then collecting the data on the field. When I worked with the algae, I tried to replicate this outside instead of just the lab. So with that, I would, anytime there was clouds or would move to a new place, I would start collecting calibration data again. In the lab, I would say because there's no change in lighting conditions because they're there, I would just start once, collect all the calibration data I need. And so I would take data from the 4 panels, save them, and then when processing the data, I would see whichever of the 4 panels is the best and then keep it. So that's what I did for the algae in the lab. But yeah.
Fantastic. And do you remember what material your panels were made out of? Was it Spectralon or Spectraflect or?
Do you happen to know, Professor? I don't.
No, it's not Spectralon. It's a cheaper material, but we did have Spectralon too. I'm not entirely sure what material is it. It's one of the panels we had from Map Air. Those they have this images that reflect multispectral images, and they use those for that. So that's what we were using.
If you do find out what the specific material is, I'd love to know.
Yeah. I'll look into it. What are they using? Yeah.
Fantastic.
I think I found it. Let me look it up.
So this is the targets that we are using, though.
So in your future work section, Ahadu, you propose using data-driven models to correct for Stella's limitations. Could you elaborate on that? And what kind of model are you envisioning? And what would you need to train it effectively?
That's something that I briefly discussed with the professor and Mattis, but it's not really my expertise or where I feel most comfortable. But I know that a lot of the research that gets this done often involves machine learning. So I was suggesting that's something that's worth exploring. But I think the way I envision it is if we're able to have some sort of model that's able to recognize how accurate stellar data is based on what you feed it. So let's say you train it enough times on actual field data that we gathered with Stella and the hyperspectral imager, and then comparing. And then once you have this trained model, take your Stella data, any Stella data, and then upload it to the system, and you get some sort of something in return. I guess some sort of like confidence range, but it's not really something I'm fully confident in and aware of. So yeah, it was just something that I thought would be nice to discuss. But yeah.
What about you, Professor? Any?
So I think the idea is the end decision that we want to make is about water quality. Even if Stella is giving us imperfect spectral observations, or with a little bit higher uncertainty than we get from a lab grade spectrometer or spectroradiometer. The question really was that even with this uncertainty, can we still get to the same end management decision around, let's say, nutrients in water? So that's where we are trying to see if we can feed that model. We can develop these data-driven models with enough samples where we can if we collect enough observation data for spectral observation with Stella and known target, known values to say water chemistry analysis, and then can we still get to a reasonable endpoint in terms of what the value should be, even if the Stella data is a little bit not accurate, or it has a little bit higher uncertainty around it, and that's really what we are trying to get to, and see if what is the confidence interval, how does it change if we use hyperspectral imager, which is well calibrated, versus Stella multispectral datasets.
From an academic and pedagogical perspective, how do you see open source, low cost instruments like Stella changing the way engineering and remote sensing, students approach remote sensing and field data collection compared to traditional high-cost lab equipment?
So I think this is tremendous and really a neat way for students to go from all the way from learning about how these microcontrollers exist and how can you combine them uh, with off the shelf microelectronics and build this cool little device, and then you also learn about all the other things that go into in integration times and saturation. Often these things are masked, especially at a very entry level. If you have a working imager, which is maybe working imager, all these things will be taken care of by the software that you're using, but you're not really tuning these things yourself. So the learning is a lot more. And not to talk about like it's accessible. It's although electronics, I think the prices are going up now, but it was around $250, which is really cheap. As compared to a $5,000 multispectral imager that you will get, even point samplers are not very not so much available and so much and inexpensive. So I think this is tremendous, and I wish we could create like 50 of these and just send it out to the whole crew. Maybe they should create it themselves and take it with them after the semester finishes. Yeah, go build one, build a sensor, calibrate it, go work with it, and then take it with you. Do whatever you want. I remember thinking, talking about this idea with few folks who work on citizen science idea things, and they were suggesting like creating a kit for libraries where we can loan it out, they can loan it out, and then people can just go and do whatever they want with it, and then come back with some observations. So there's lots of ways even beyond engineering or graduate education where you can kind of use it. I cannot say enough about it. It's a great device. It's a really good introduction to many of people to microelectronics programming. Even I think using circuit Python, is that what you're using? And all those things. It's really cool way to get into those things.
Ahadu, what do you think?
Yeah, so I think just the idea of involving citizen science is perhaps the most interesting thing I have about STELLA so far. And I say this because I have the feeling that a lot of people tend to underestimate how important Earth observation is, and also how important and at the same time difficult and inaccessible it is. And so being able to work on making this technology more accessible, especially through citizen science, because at the end of the day, we can have a whole team of scientists, researchers in the US universities, or all sorts of countries, but being able to give this out to everyday citizens that can use this every day is ideally, is I think the ideal we should strive for. Because I can definitely imagine a farmer would definitely appreciate having a sensor for just as cheap as $200 and know if his plants and stock is going to survive some sort of monsoon, knows if it's affected or not. And so being able to make this technology more accessible is, I think, very important and the most interesting part about STELLA.
Well, cool. And in that vein, so the next question is basically connecting this to your work with Engineers Without Borders, which often discusses and focuses on sustainable community level solutions. What do you see as the biggest real world hurdle to putting a tool like this into the hands of a local farming cooperative? Is it the cost, the expertise needed to interpret the data, or something else entirely?
I'd say first is being able to make this universal and easily usable for everyone. And so coming up with actual good protocols that makes it easier for anyone to just pick up the device and use it and obtain quality data. So the angle at which you put the device, how up or down needs to be the different settings. And so being able to transmit all this knowledge and make it accessible first. Because at the end of the day, STELLA is just, you just press the button and you get the data quickly. But I think first of all, the first challenge is drafting and having an actual proposal and protocol for when we go out and collect field data. And so if we're able to get quality field data out of this.
Ahadu, this project required you to wear two hats, the scientist interpreting spectral signatures and the engineer understanding sensor limitations. Can you share a moment where a scientific goal forced you to be creative with the engineering, or an engineering constraint made you reevaluate your scientific approach?
I think the main thing I noticed was working with satellite data and trying to incorporate that part, and noticing that I would get really good data with the hyperspectral imager and STELLA because I was able to get very close to the leaves, or with the hyperspectral imager, zoom in and get any sort of reflectance plot that I wanted. And then when I tried to do this with satellite data from Planet Labs, I would get a square of about, I think, 9 meters squared in surface. So what it just ends up doing is just it mixes up all the reflectance data, averages it out, and gives it out for that box. And so I wasn't able to really, and I was able to notice how inconsistent the satellite data was from the Spinach data. And unfortunately, it was too late for the semester for me to present and rework on integrating satellite data. And so what I realized is if I want to get actual quality data for plants, I would need to have large cover, like big. So yeah, the biggest challenge I faced with integrating satellite data with STELLA was how different the surfaces I was getting. How different the, let me restart, sorry. So when integrating satellite data with STELLA, I noticed that I would get a square of 9 meters squared for all my wavelengths for my reflectance plot, and so it would average out all of that surface into one big plot. And so when I was still in the hyperspectral imager, I was able to get very precise data points because I would either be very close to the leaves, or I was able to zoom in and get the right pixels I needed. And so the next step, what I would have to improve and work on would be finding a larger cover of land that's covered with the same consistent material. So if I'm working on leaves or trees, find something where I would have at least 9 meters squared of the same consistent material all across that pixel, and then use it with STELLA or the hyperspectral imager. And so that would be one way of fixing my previous approach. And so maybe working with Spinach Leaves wasn't the best decision, and maybe moving to something bigger like a forest might, or bushes might be better.
Well, and Professor, I guess I would also ask you if you had noticed any different, basically where, science helped, with something and or that the engineering didn't, or the engineering and vice versa. Basically the same question that Ahadu had, but if you noticed any of these types of things with these trade-offs with the Stellas.
Nothing comes to my mind, but I think the spectral resolution that what Ahadu was getting to, the point versus imager, so I think the idea was that it's an imaging spectrometer, the hyperspectral imager that you're looking at, and now you're all of a sudden committing trying to understand this to compare this to a point reflectance. So the question, it's an interesting engineering problem to how do you compare the data sets, because we were working with pure pixels mostly big enough. So that again, that same thing that Ahadu was talking about, there were times that you were using mixed pixels. It would be fine enough with the hyperspectral imager to do it, because they are really close enough. You can get centimeter resolution, or even 10 millimeter resolution. But even with STELLA, very close up, it's not getting the pure pixels. So that was kind of an engineering problem with. I think eventually we solved it by using bigger, by basically changing our target. So, but I now that you have talked about it, it might be interesting to look at if we place the engineering solution might be to actually just place a tarp which has almost no reflectance. So now you have created some sort of and you know how much area you are covering, so you can kind of scale it, and figure out what's going on.
So you've established a solid baseline for how Stella performs in a traditional agricultural field. So let's imagine you need to deploy a similar sensor network in a much more controlled environment, say like a greenhouse or a vertical farm, where every input is meticulously managed. How would your strategy for validating and using the sensor data change in that kind of closed loop system?
So I think maybe we're able to get, so if the goal is to compare with hyperspectral imager, I would say maybe just scale it down and find another device. But one thing I'd have to say is see if we get consistency between different Stella data sets. So if we're able to use different Stella sensors, so how maybe repeat the same experience for 3-4 times and see if we actually get quality data. And then perhaps simulate the experiment in another setting that's more comfortable to using an aerial imager, for example. But yeah, I would say maybe using different Stella devices to see if we're able to get consistent data between between the different devices first. Yeah.
Fantastic. And your thoughts, Professor?
Yeah, so I think it's kind of interesting. If you have a very controlled environment, I suppose your objective changes, right? Now you're looking for anomalies, as Ahadu was talking about. So it may be interesting. I'm thinking of a tomato farm with irrigated with everything controlled, lighting controlled, and everything else. And now all of a sudden, all the Stellas are looking at your plants, and you have not acres, but a lot of land that you can manually go through everything. You're looking for calcium deficiency in one of those. So if you find few anomalies like abnormal reflectance, and this could be automated, every plant could have its own sensor looking at it. And then that would be cool to look at, just anomalies and trying to figure out where out. And then think of that as a like I guess what do you call that? It's automation for agriculture folks. But yeah, it will be pretty cool. I don't know much. Doesn't answer your question, but just haven't thought about it. Let's put it that way.
Looking at what Ahadu has achieved with this baseline comparison, how does this specific project inform your lab's future roadmap for future Earth observation technologies or upcoming experiential learning missions? I know you already talked a little bit about it, but you can go in further in depth, possibly.
I almost I think my lab and I'm very interested in trying to use Earth observation particularly for inland water resources and trying to understand small ponds and the chemistry there. I feel that one of the limiting problems there is a lack of data sets on water chemistry and also data that can help us validate what satellites are observing. So it seems like what Stella can do, and I'll make a case for. I guess it's a nice case where you can use existing citizen and community science projects and give them a stellar observation, and then you can all of a sudden you have a lot of data for lots of different ponds around the United States or even around the world tied to the overpass, and then all of a sudden you have a way to validate those things, and that's really, to me, it's a really powerful tool. Of course, we need to validate that this actually works very well, and anybody can use it, which I think is a reasonable expectation. Yeah. So that's where I think we are going to try it, and hopefully we'll figure out some way to get this working.
Fantastic. Yeah, we like to call it opportunity resolution.
Yeah.
Yeah. So people have the opportunity to gather the data as much as possible.
Yeah.
Okay. And then this is the final question. And again, I want to thank you all very much for your
Thank
time.
you. Yeah, thanks for doing this.
But finally, Ahadu, thinking about the big picture of making Earth observation more accessible, what in situ application for a sensor like Stella excites you the most personally? What's a new scientific question you'd be excited to answer if you could deploy, say, thousands of these sensors? I know we touched a little bit on it, but
So yeah, I think this brings it back to what we discussed about citizen science earlier. If let's say we're able to deploy thousands of Stellas in a specific region, I think it would be really interesting to see if we're able to mimic what we get from satellites using Stella. And if that works by having thousands of Stellas where we collect thousands of data points every single day, it allows us to, first of all, perhaps calibrate satellite data, all the missing data sets that we need of in situ data for satellites, and just the idea of making this cheap and accessible is, yeah, the most interesting part. So yeah, I would definitely say just deploying it out and then see if we're able to get similar data as what we get from a satellite or a hyperspectral imager, for example. Yeah.
Okay. And same question for you, Dr. Saurav.
So I think I'll just hop back to the last answer. And really, I feel like if you have thousands of Stella and if you can fill that water quality gap, and somehow we figure out that you can measure water quality in small ponds across the United States using Stella. And maybe it's like I remember seeing a cuvette one where you have a cuvette, you add some and point it up to the and measure the reflectance, and that gives you the nitrate, the DOM, the phosphorus, and do it around the time that your satellite is passing. Now all of a sudden you have a very rich data set where you can now create the link your satellite observations to on-ground measurements. Maybe it's a point measurement, and we can figure out maybe they make 10 measurements and combine them together. So that creates a rich library that can be used eventually to monitor long term.